So continuing from the last lecture, we are deriving solutions for fixed volume gravity current. So we are considering that a fixed volume of gravity current is released and it is actually expanding horizontally and shrinking vertically, right? And here we have defined two regimes, regime 1 and regime 2, where early regime is when Reynolds number is much greater than 1, and that actually means that inertia force is much greater than viscous force, right? That is how we define Reynolds number. And regime 2, that is at late times when gravity current has been moving for a long time, your Reynolds number actually decreases and becomes smaller than 1. And why is that? Because your velocity is decreasing, right? And gravity can become slower and slower with time. So when it becomes slower, what happens is your viscous force becomes dominant, or it becomes more dominant than the inertia force, and its value becomes much greater than the inertia force, and in that case we neglect the inertia force and consider the viscous force, right? And buoyancy force is something that is there all the time because that is driving the force, and that is why in regime 1, that is early time, your buoyancy force is balanced by the inertia force. In regime 2, buoyancy force is balanced by the viscous force. Okay, so we have three different kind of forces and we are trying to find their dimensionally equivalent form, and we use this equation, Navier-Stokes equation, for finding these three forces. And we know that this equation is defined as force per unit volume, so we integrate this equation for per unit volume, and we find all the forces one by one. So here a phi is the inertia force, and when we do this integral we get this equation number 1, which we are going to copy now. Okay, and then we have buoyancy force, that is equation number 2, and also we have viscous force, that is equation number 3. Okay, so we are now going to solve for regime 1, or regime A as we have named, early time gravity current, where Reynolds number is much greater than 1. Okay, here we balance if inertia with F buoyancy, okay, or Fi equivalent to Fb, right? That is something we have defined previously. So now we get this from equation 1 and equation 2. So this is basically equation 1 is equivalent to equation 2, and we have already copied equation 1 that looks something like this, and that is equivalent to equation 2, which gives us this particular equation. All right, so this is what we have when we balance a phi with a b. And what do we see here? There are some common terms which may neglect. For instance, this w cancels with that w, and this row cancels with that row. Okay, and this gives us, and we can now pull xn to the left and put t to the right, and that will give us xn to the power 3 is equivalent to, here a naught also cancels this a naught with the square, so that becomes g prime a naught n t square, right? So that is what we get. And now if we again simplify it little further, this will give us x naught is proportional to g prime a naught to the power 1 by 3 t to the power 2 by 3, right? So what you see here is the length of the gravity current increases with 2/3 power of time in the early regime. Okay, so this actually says that xn is proportional to t to the power by t to the power 2 by 3. Okay, And what we can do here is this can be written as, we can now remove this equivalent form, and we can use a constant to convert that into equal form. So let's say that is C1 G prime A naught 1 by 3 t to the power 2 by 3. Okay. So now what we see here is that this equation tells t equal to 0, xn is 0, which actually is not true, because we saw that this starts with certain volume, right? And that is why this equation either works for xn to be infinity at t equal to 0, that means your, sorry, xn to be 0 and h to be infinity, so that is something that can be assumed. Or other thing we can do is, so this is assuming xn tends to 0 and h tends to infinity at t equals 0. So that basically gives us a naught equals not 0, right? So this is one way to define it. Other way is, we can say t equal to 0, xn has some value. So we can say that this equation works for you know some reference point that is given as a naught 1 by 3 t minus t1 to the power 3. And let's see what exactly these terms mean. C1 g prime a naught 1 by 3 t minus t1 2 by 3. So this is the equation that we get for the gravity current length. Okay, where xn is equal to x1 at t equal to t1. So that is basically our reference point from where we started measuring the gravity current. Okay, because at t equal to 0, if theoretically we assume xn is equal to 0 and h infinity, then it will work. But otherwise we can assume that at t equal to 1, which is the reference point, the length of the gravity current is xn, and then it increases in this particular manner, where it is increasing with 2/3 power of time. Okay, and other thing that you will note here is C1 is a constant which can be found experimentally, which again we are not able to do it in the current lecture, but this is an experimental constant. But this is a constant, not really a variable. Okay, but this equation at least shows us the rate of change of xn with respect to time. Okay, and c1 depends on channel depth and surface, etc. So it depends on many parameters, and channel depth is one of the parameters, because in some of the videos, for example, some of the images, as we have seen here, if channel depth is limited, then basically there is a backflow, and this that affects how the gravity current will flow, right? So it depends also on the channel length, channel depth, etc. So this C1 is a constant for a particular channel, but not constant for throughout medium. Okay, and that's why we are not really defining a fixed value for this constant. Okay, so this equation actually works for early time gravity current. Okay, and this also gives us the velocity. So if you want to find the velocity of the gravity current, that is, let's say u, how do we define u? That is dxn over dt. So basically u will depend on, or let's say this will be equivalent to uh, okay, if we don't consider other parameters. Okay, so This will be roughly equal to C1 G prime A naught 1 by 3 dt 2 by 3 over dt. Okay, so U is 2 by 3 C1 G prime A naught 1 by 3, and that will become t to the power minus 1 by 3. So basically 1 by 3. So this is the gravity current velocity uh, in early stage, where you can see U is proportional to t to the power minus 1 by 3. Okay, that is the velocity. Early stage velocity, right? And we have seen in previous case that for constant continuous flux, velocity remains constant, where in this case you can see how velocity is decreasing with time, right? It is decreasing with 1/3 power of time. Okay, so we have analyzed the early time stage. Now let's look into regime 2, regime B. Late time gravity current. Okay, where Reynolds number is much smaller than 1. Okay, and in this case, like in previous case, Reynolds number was much greater than 1. Here it is much smaller, and that is why if buoyancy is balanced by if uh, a viscous force, right? Or in other words, AB is F mu. Okay, and these two again we can get from equation number 2 and equation number 3, where let's first copy the equation number 2, that is this one. And this is equation number 3. Okay, and now again we will do some simplification. We can cancel this W, and we can actually put the x3 term to the left and other things to the right. So this will give us xn to the power 5 is proportional to rho g prime a naught cube times t over mu. Xn to the power 5 is proportional to rho g prime a naught cube times t over mu. Okay, so this is what we have got, and let's analyze it further. So here we have to note that this mu is a dynamic viscosity, right? So mu is the dynamic viscosity, which can also be written as rho times nu, right? Where rho is the density and nu is the kinematic viscosity. Okay, so we can actually, all right, we have I think made one small mistake here in equation number 3. Okay, I think this is all right. There is no mistake. So mu can be replaced with rho nu, and we will get equal to rho g prime a naught cube over t over row new, and row here cancels with the other row, and this gives us equation of this form: xn to the power 5 is proportional to g prime nu a naught cube over t, right? And then this equation again can be written as xn is proportional to g prime by nu to the power 1 by 5 a naught to the power 3 by 5 and t to the power 1 by 5. Okay, so now we will again simplify this equation by including it as c2 g prime by nu 1 by 5 a naught 3 by 5 t to the power 1 by 5. Okay, but this equation again means that valid if xn tends to 0 and h tends to infinity at t equal to 0, right? But that again is not true, because particularly we are solving for late time regime where gravity current has already seen the early stage gravity current, and that's why this can be replaced once again with xn minus x2 is equal to c2 g prime over nu 1 over 5 a naught 3 over 5 t minus t2 1 over 5. Okay, so this will give us xn to be equal to x2 plus c2 g prime over nu 1 over 5 a naught 3 over 5 t minus t2 over 1 over 5. Okay, so this is the gravity current length, at late times. Okay, this is how the length of the gravity current changes with time at late times. At once it has become much thinner and longer. Okay, where x2 or in other words xn is equal to x2 at t equal to t2. That is the reference point for the late time regime. Okay, so let's assume that your gravity current starts at x2, late time regime starts at x2, and you have the time measurement as t2. So if you add x2 and t2, this equation will work. Okay, and here again, if you want to find the velocity, so gravity current velocity u will be dxn over dt, and because other terms are constant, so this will become c2 g prime over nu 1 by 5 a naught 3 by 5 and 1 by 5 will come here, and it will become t to the power minus 4 by 5. Okay, so here, or in other words, we can pull the t to the power 4 by 5 here, and that will replace this one. So this is the gravity current velocity. Okay, so you can see how the gravity current velocity is decreasing in time, and now the factor has become greater in the denominator, so it is decreasing much more slowly. In the beginning it slows down faster, but it slows down slowly later. Okay, so velocity at late times. Okay, and once again c2 is an experimental constant specific to the channel condition. Okay, so we have derived the position of the gravity current at early time and late time for a fixed volume gravity current or gravity current at shutdown stage. Once, let's say, gravity current is running with continuous flux, but if you stop the injection, stop the influx, then gravity current will still continue to move, but it will follow this kind of uh, profile for xn and velocity. Okay, and if you want to plot the rate of change of or position of gravity current, so let's say we want to plot, so if this is your xn, this is your time. So when gravity current is getting injected with continuous flux, then in that case it will just go linearly, right? As we have seen in the previous model, where you can see the velocity is constant, you don't see it as a function of time, right? Velocity is constant in case of continuous injection, and that is why if velocity is constant, your xn will simply increase linearly with time, right? So xn is proportional to t to the power 1, where u is constant. This is when uh, it is still the continuous injection. And once you stop the continuous injection, this will now decrease with xn to the t to the power 2 by 3, as we have found in this case. That is the velocity, and this is t to the power 2 by 3, right? That this factor. So that xn is now decreasing, so it's increasing with 2 by 3, factor of 2 by 3, right? So here it will be 2 by 3, and then basically xn is not really increasing with t, so velocity is basically decreasing. Okay, so that is let's say second zone, and now the third zone can be like this, where xn is proportional to t to the power 1 by 5. Okay, where here u is in this case is proportional to t to the power minus 1 by 3, right, as we saw in case 1, and in this case u is proportional to t to the power minus 4 by 5. Okay, so these are different zones we have, and if you want to define, you can call this as this point as x1, this as t1, and this point can be called x2 and t2. Okay, where we assume this zone as continuous injection, and from here is the shut down stage. Okay, so this is how a gravity current flows and evolves. It increases, the length increases with respect to time linearly in the beginning when there is continuous injection. That means your velocity is constant, but the moment you stop injecting denser fluid, it increases with 2/3 power of time, and then velocity starts decreasing with 1/3 power of time in the beginning when Reynolds number is still greater than 1, and then once at late times when it has slowed down significantly, Reynolds number becomes smaller than 1, and that is when your xn now increases with 1/5 of time, and velocity decreases with 4/5 of time. Okay, so this is the complete behavior of the gravity current. As you can see how it goes from very early time till late time, and now this kind of model can be used to predict gravity current behavior in atmosphere and in channel like here, or in this kind of gravity current that we analyzed previously, right? Like here we saw some different examples of gravity currents. So these solutions can be used to model this kind of gravity currents and understand their flow, which will give you the velocity, the height profile, height value, and also the g prime value, the density difference between the gravity current and the ambient fluid. Okay, so you can see how your, in all these cases, your g prime value plays an important role, right? That is the velocity and that is the g prime value, and a naught here in this case is a constant, that is the initial volume of the dense fluid. Okay, so we will stop the gravity current lecture here, and in the next lecture we will start a new topic.